going to hand over to Dr. Steve Barrett from Liverpool University, who is going to talk to us about the nature of light.
Thank you very much. Thank you, and thank you for the invitation back to talk to Liverpool AS once more. I've got a number of demonstrations here as well as some PowerPoint slides to show you, and I'm going to be flitting backwards and forwards between the two, and at various times I'm going to probably ask for the lights to go down. I hope that's not a problem for anybody. Can we just double check what it's like with the lights off at the moment?
Supernova.
Is that okay for everybody, or is this too spooky? Is this okay?
Yeah, we're astronomers.
So, yeah. Good point, I've forgotten that. So it's not important that you see exactly what's going on this table at the front, because I've got a camera set up such that hopefully you'll be able to see on the big screen what it is I'm trying to show you, okay? And some of these demonstrations, in order to try and keep this to within an hour, because when I've given it before it's tended to go a little over an hour, what I'm going to do is to skip over some demonstrations and invite you to come to the play table over here and have a look at the demonstrations for yourself. Rather than me demonstrate them up here, I'll just say one or two words, and after the break, after you've had your LAS business, I'll invite you not only for Q&A if you so wish, but I invite you to come down and have a play with 4 sets of demonstrations that I've laid out on the table to your left. Okay? So I will be skipping through some of these. So for the time being, we can leave the lights as they are, and then I'll ask them down in just a second probably. So, Fiat Lux. Fiat Lux, as you saw probably from the rolling display at the start there, let there be light, or if you read it in the original Hebrew perhaps. But there it is, in the middle of the University of Liverpool logo, there is Fiat Lux, let there be light. Some students not so much trained in the classics assumed that Fiat Lux was in the University of Liverpool logo because those were the 2 sponsors of the university. And then we had to point out that no, it was Latin, but never mind. Okay, so what I'm going to be talking about is the nature of light and the colours of light, and a little bit about atoms and light. And if it looks like I'm running a little bit over time and you're dying to have a cup of tea, I might go fairly rapidly through that last bit. But I'm keen that you see a number of these demonstrations. So there will be PowerPoint. Okay, I'm not wearing a tie, and there's more than 5 of you in the audience, but that's just to remind you that we're switching from a demonstration back to a few PowerPoint slides. And that also helps if you, at the end of the day, if you wish to take away a handout, it's most important to know whether I was speaking at the time or whether I was giving a demonstration. So the 4 demonstrations are measuring the speed of light, measuring the wavelength of light, looking at the colours of light, and looking at the polarisation of light. And in the handout, as well as in this talk, I'm going to use these little icons to remind you where we are, so that if you open up the handout, for instance, and you see these vertical lines, it reminds you that we're in the middle of the colours of light demonstration. That's the idea. Okay? So let's start with a few PowerPoint slides before we kick off the first demonstration. It's a warm summer evening in ancient Greece. I've always wanted to start a talk that way, ever since Sheldon did when he was trying to teach Penny some physics. So where does, the idea of what is light obviously has been around for a few thousand years. Back in a few hundred years BC, it was assumed that everything was made of earth, air, fire, and water. And so how do the eyes work? How does vision work? Well, clearly there's fire in the eye which shoots out of the eye, and that's how we get vision. If you think the idea of light emanating from your eyes rather than being received by your eyes, if you think that's a very odd concept, bear in mind that anybody who's ever seen an animal at night will know that animals' eyes glows, and therefore it's not unreasonable to think that perhaps light does come out of the eyes. Of course, now we know that the light is simply a chemical receptor, if you like. Light coming through the lens will hit the retina, cause a chemical change, and that's how we perceive vision. And of course, light from different parts of our field will arrive at different parts of the retina. But that doesn't explain what the blue lines actually are. What is light? And of course, that's been a question for scientists over many centuries. Isaac Newton here, back in the 1660s. You see him in his rather fancy dress there, trying to reproduce the Pink Floyd album cover by putting a prism up to a chink of light in his study and producing a spectrum. So yes, we know that Isaac Newton used a prism and showed that white light was made up of colours, but he did far more than that. And there was an argument raging back in the 17th century as to what should we, how should we treat light? Should we treat it as a wave, or should we treat it as a stream of particles of some sort, the so-called corpuscular theory. There were people on both sides of that argument. It's only now that we realize with quantum mechanics, well, the answer is it a wave or is it a particle? The answer is yes, it is both. But that's, of course, was beyond Newton at the time. We're going to spend most of this talk demonstration thinking about the wave nature of light. So light as a wave. Whenever light passes through an aperture, whether it be a telescope or a microscope, or whether it be a slit, a small slit, relatively narrow, then its wave nature will be revealed. So let's just make sure we know our nomenclature. We're going to be talking about crests and troughs of waves, and we can think about water waves if we want an analogy with a light wave. And a wavelength is from one crest to the next crest, or if you like, one trough to the next trough. It really makes no difference. That's what we mean by the wavelength. And I'm sure you know, but we're about to find out, that we can measure the wavelength of light, and it turns out that the blue end of the visible spectrum has a wavelength of a little less than half a micron, or 400 nanometers, and the red end of the spectrum has a wavelength of about twice that, about 700 nanometers, or 0.7 microns. So we're going to be looking at that in due course in one of the demonstrations. And again, just for context, a reminder, again, you all know if you're astronomers, that the visible part of the electromagnetic spectrum, of course, is only a part of the whole electromagnetic spectrum, running from gamma rays, X-rays, through ultraviolet, then through the visible, and then infrared, microwave, radio. So I'm talking about the nature of light, and I'm using demonstrations that are based on visible light so you can see what's going on, but the principles apply to any light, whether it be gamma ray light or radio light. We don't, of course, talk about radio light, we just talk about radio waves, but it is just another form of light. And some light reaches the Earth's surface, so you can see why we've evolved eyes that see in the visible, because most of the light actually makes it through the Earth's atmosphere. Gamma rays are blocked, but there's a sort of window, if you like, in the atmosphere that allows visible light in. Some radio waves are allowed in as well, but if we wanted to see objects in other wavelengths, for instance, here's the Crab Nebula seen at different wavelengths, radio, infrared, visible from the Hubble. If we want to see it in other wavelengths, we have to send satellites up to get above the Earth's atmosphere. So I'm not talking about how we use light in astronomy. This is about light itself, this particular talk. So let's start with wave interference. We can see two waves. One happens to be static and the other moving. It doesn't really matter. This is just for illustrative purposes. If two crests happen to line up, then the two waves interfere with each other and reinforce to give you a bigger wave. If the crest of one wave lines up with the trough of another wave, as happens here, then we get cancellation. We would call it destructive interference, but let's just call it cancellation of the waves, and hence we get nothing. So this idea that waves can add together or subtract, if you like, and either reinforce each other or destroy each other, this is what we call interference. And interference is something you've seen before, even if you didn't realize it. Whenever you're looking at colors in a soap bubble or an oil film, you're looking at light that's traveling through very thin layers, and the effect of interference, certain colors, certain waves of certain wavelength reinforcing with each other, and perhaps other waves cancelling each other out, giving rise to these rather spectacular colors that you see in soap bubbles or oil films. Now, one of the most important aspects of what I've just told you is the fact that we can generate standing waves as far as this demonstration is concerned. Standing wave is what happens when a wave is traveling in one direction, for instance left to right, meets another wave traveling right to left, the same amplitude, the same wavelength, the same frequency. Now you can see that every once in a while the two crests line up and you get a very big wave, and every once in a while they cancel each other out. But notice that the resultant wave is neither moving to the left nor moving to the right. That's why we call it a standing wave, not because it isn't changing, but just because it isn't traveling to the left or the right. And what we notice is there's some points, like this point here that's going up and down. These are hotspots that see a very big change in the wave. If this was a cork on the ocean, that cork would be bobbing up and down quite a long way. But there are other points, like this point here to its left, which are nodes or dead points. In other words, if you place a cork there and have the wave being generated, that cork wouldn't be going up and down. So some parts of this distance scale along here will see a significant variation in this wave, and others won't. Why is that important? Because we can actually use that to actually get an idea of how waves behave. So for instance, what we can do is generate standing waves, and if we generate standing waves, for instance, in an object, then parts of that object will get hot because the waves are going up and down and actually making the atoms or the molecules in that substance move, and other regions will remain cold. If we're using a microwave oven, for instance, if we send microwaves through food, some parts of that food will get piping hot because they correspond to these points here, and some parts of the food will remain completely uncooked because they correspond to the nodes that we see there. One thing to notice, if you remember what the wavelength definition is from one crest to the next, not only do we have a hot spot here, but we have a hot spot there as well. There are 2 hot spots for every wavelength. That's important in what's about to follow. Because we're going to actually now measure the wavelength, we're going to measure the wavelength of light in order to measure the speed of light. So what are we going to do? We're going to do a demonstration. This demonstration is a bit of a cheat because this is a Blue Peter demonstration. In other words, I thought it would take a few extra minutes and I didn't want to waste too long by trying it live, so I tried it this morning, and this is what I actually did. And you can try this for yourself if you want to take the instructions home and try this for yourself. Take a microwave oven. Remove the rotating turntable, because what we don't want to do is to have the food rotating and blurring out the effect we're trying to see. Put a chocolate bar in the microwave oven. This happens to be Sainsbury's. Other chocolate bars are available. Put the chocolate bar into the oven. It works for, in principle, any food, but it's more visible in chocolate, the effect we're looking for. You can do it with cheese, but it's not as clear, and it's a waste of cheese. And so this gets the Wallace and Gromit thumbs up of approval. So we're going to stick with chocolate for the time being. Put the chocolate in the microwave and zap it for a length of time which is difficult to be precise because it's different for every microwave. I tried sort of 10, 15, maybe 20 seconds. And then you will find that you end up with, if I can do this without breaking the chocolate, you end up with hot spots. So I will put it back in its packet and let you have a look at that if you wish to pass that around. You quite definitely, I'd like it back, please. Yes. And just to convince you it wasn't a fluke, there are other examples here. I zapped it a few times just to make sure it worked. So what you find is, you find the chocolate melts in particular points, these hot spots, 2 for every wavelength. And that is, roughly speaking, what you will see when the chocolate actually gets handed around. Whether it melts slightly or whether it melts through depends on how many seconds you zap it for. But there are clearly areas that are melted and the rest of the chocolate is as solid as it always was. And remember, 2 hot spots for every wavelength. So if I measure the distance between those hot spots and it turns out to be 6.5 centimeters, that means I know the wavelength of the waves traveling through the microwave were 13 centimeters, simply by taking that value and doubling it up. So the wavelength of the microwaves in this particular experiment, the light waves in this experiment, the wavelength was 13 centimeters, which I've measured. Having measured the wavelength, if I know the frequency, then I can work out the speed of light, because the speed of light is just how long is the wiggle multiplied by how many wiggles per second, i.e. the frequency, how often it goes up and down. Luckily, we know the frequency of microwaves because every oven has got it written on the back. If you didn't know that, turn your microwave around or take it out of your built-in kitchen and have a look on the back, and I have a Daewoo microwave and it runs at a frequency of 2,450 megahertz, 2450 million cycles per second. And so if I take the wavelength I've just calculated from the chocolate by doubling that distance, multiply it by the frequency, which I've read off the back of the oven, I get the speed of light is 320,000 kilometers per second, according to that calculation. Now, we know the actual speed of light is closer to 300,000 kilometers per second, but even Gromit is impressed with the fact that we can get it to within 10% just by putting chocolate in a microwave, hitting the go button for 10 seconds and making a very simple measurement and then a calculation. We can actually measure the speed of light. The speed of light, I might add, is the same for every electromagnetic wave. Gamma rays go at the same speed as X-rays, go at the same speed as UV, infrared, microwaves, visible. All electromagnetic waves travel at what we call the speed of light, 300,000 kilometers per second. So, not a true demonstration in the sense that I did it earlier and I'm now showing you the result, rather than attempting to do it live, which would take just a few minutes extra, but I invite you to try the same thing for yourself. Not with this chocolate, go buy your own, and then put your own chocolate into the microwave. I tried it with 2 bars, one above the other, just to see how many hotspots I could see, and clearly there's a few different places where it's melted, and I worked out that that was 7 centimeters and that was 6 centimeters. There is a little bit of variation. You can't get the speed of light precisely to 6 decimal places by this particular technique, and the exact pattern of the hotspots will depend on the microwaves. The microwaves are generated in the oven, sent through the food, they bounce off the wall the other side and come through again, which is why you get standing waves. But it also bounces off the roof, it bounces off the back, it bounces off the door, so it can get a little bit complicated. But with a little bit of trial and error, I'm sure you'll find somewhere you can place the chocolate so you can get your hotspots and hence prove what the speed of light actually is. It is possible to zap it for too long. I tended to zap it for a few seconds, see if it's melted, if not, a few seconds more, see if it's melted, a few seconds more. But you can go overboard on this sort of experiment. Not really. Don't give it 20 seconds and then say, damn, I wish it was less. Work your way up. And having more than 1 bar means you can make a mistake and go back and try it again. Okay, so there's demonstration number 1. We can measure the speed of light, and it turns out to be really fast. Hence, Galileo had a problem trying to measure the speed of light by uncovering a lantern and then having somebody else a long distance away. When they saw the lantern uncover their lantern, it was very quickly realized that the speed of light is really fast, and too fast to actually use human reflexes. But with a bit of ingenuity, you can measure it for yourself. Right, back to the PowerPoint again. Remember I said we can add waves together and we get interference. They either reinforce or destructively interfere with each other to either make a larger wave or cancel the wave out. Another definition, which is a little bit confusing, is when lots of waves interfere, we call it diffraction. Why have 2 words for the same thing? Well, that is a little bit confusing. Interference of light is just, do the waves add up or cancel each other? But it just so happens that under various circumstances, we don't just have 2 waves, we have lots of waves, maybe millions, billions, trillions of waves interfering with each other, and we have just chosen to use a different word to describe that situation. There's nothing different physically about diffraction compared to interference. Diffraction is just interference of lots of waves, but it still confuses people in that respect. But we know about diffraction in the astronomical sense because I'm sure a lot of you are aware that when you're looking through a telescope at a distant object, the resolution you can see, the sharpness of what you're looking at, is determined by diffraction. It's determined by the interference of waves going through the telescope. So we don't normally notice diffraction unless, for instance, we're looking at very high magnification of stars through a telescope or objects through a microscope, or possibly light travelling through a narrow slit, a slit that's larger than the wavelength of light, but quite a small fraction of a millimetre. I tested this for myself by sending light through a slit to see if I could actually measure what's going on. A wide slit produces very narrow diffraction bands that you can hardly see, which is why a large mirror or lens in a telescope is a good idea, because diffraction effects are then limited. Whereas if you send light through a narrow slit, the diffraction fringes are larger and more noticeable. So let's have a look. I sent light through a narrow slit. I simply took 2 pieces of cardboard and brought them together so that they were separated by the thickness of a piece of cardboard. You can have a closer look at it later if you wish. It's just this here. 2 pieces of cardboard separated by the thickness of a piece of cardboard, which is approximately 0.14 millimeters. I let sunlight fall through that slit and simply took a photograph of the sun that arrived on the other side. And it doesn't look like anything in particular, but if you increase the contrast of that image just by bunging it into your graphic software and playing with the contrast, you see the sunlight comes through, but on either side of the slit you get dark light, dark light, dark light, dark light. That's what I mean by fringes. You get this zebra effect on either side of the slit. And that will always be there whenever light travels through an aperture. Whether it be a large aperture or a small aperture, it's simply more difficult to see. If you have a nice, large telescope mirror or lens, you tend not to notice it. If you have a small telescope or a small slit, then the diffraction effects, these zebra fringes, are more noticeable. And that's what you would expect a star to look like. The intensity of a star is not a delta function. It's not just a spike. It's a function with a given width, and around the star you will see these ripples, like ripples in a pond. If you're looking at a star through a telescope with a circular mirror, and virtually all mirrors are circular, all lenses are circular, they will produce circular diffraction rings like this. So, second demonstration, and this one is going to be live, and let's see if this works. What I'm going to try and do is measure the wavelength of light in real time here. I've got a laser, just like this laser, but it's just a slightly different shape, that's all. It's just a laser that's bolted onto a retort stand here, and I'm going to see if it's possible to actually measure the wavelength of light. So the light's down in just a second, please, if you prepare yourself on the switches there. Let me just get this set up first. Okay, what I'm doing is sending the laser through two cardboard slit, two pieces of cardboard closely spaced together. Laser, cardboard, nothing, 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 screen. And don't bother about looking at the screen because I've got an iPad here that's staring at the screen. So, could I have the lights off, please? Let me switch from PowerPoint to the iPad. Okay, I hope you can see that it's possible that you can see on the screen, but you can't see what the hell I'm doing, so let's see if it makes a difference if I come up here. You can see a rather wide strip of light here. Let's ignore what's going on above and below. That's a little bit spurious. I'm interested in the fact that there's a very wide patch of light here. Then it goes dark in this region here. Then it goes light again. Then it goes dark. Then it goes light again. Can everybody see that okay? Yep. And it's the same on the other side. Very bright in the middle. Then it goes dark and the light disappears. Then it goes bright. Then it goes dark. Then it goes bright again. Let's see if I can step off the stage without breaking my neck. Okay. So in other words, what we're actually looking at here is a variation of very bright light in the middle, but then we get these ripples, these zebra fringes either side. Just like when you look at a star, you see a very bright star that's hopefully a nice pinpoint star through your telescope, but around the telescope you'll see dark light, dark light, dark light. How many of them you see depends on how bright the star is and how well collimated your telescope is, etc., and exactly what the aperture is of the telescope you're looking at. What I would like to do is to measure how far it is from when it crosses this central line here, when you get the wiggles in the light, when do they go through zero? I would like to measure those, but that's actually very difficult because, of course, I would like to be able to measure 1, 2, 3, 4, 5 of them, and they get rather faint rather quickly. Let's just remind ourselves what we're looking at. If we go back to the camera again, I would like to measure the distance between where the light disappears to where the light disappears to where the light disappears, but that is a rather difficult measurement to make. But rather usefully, it is possible to actually make a different measurement. Rather than measure these distances here, I can measure the distance, the width of this central peak, which is twice what I want. And so if I measure the easy one, the width of that central peak, and divide by 2, that gives me the number I want, how far it is between all of these zeros, all of these dark parts of the zebra fringe. If I can calculate that, then I can use that to measure the wavelength of light. So that's what we're doing. And just to prove, in case you're in any doubt that that is a live image, let me just put my hand in front of it so you know it's not just a picture I took earlier. Okay? Yeah. So this is a genuine demonstration, not a Blue Peter demonstration. Okay, so we saw something like that, a very bright region here, dark light, but it's very difficult to see those others. And so what we're actually going to do is measure that. And let me just make sure that if I've set this up correctly, then you probably can't see the ruler, but I'm going to double check how wide that is. It's a little bit more than 3 centimeters in this particular setup, because I think I've got the distance from the laser to the screen a little bit more than I intended it to be, about 3 meters. So the width of that, which is twice the number I actually want, is 3 centimeters. How do we use that to measure the wavelength of light? Well, the size of these zebra fringes depends only on 2 things, the wavelength of light and the size of the slit the light is going through. It's the wavelength of light, the size of the slit, that determines how wide this zebra pattern is. In other words, if we look at it from above, then the light is travelling through a slit. This slit is 0.14 millimeters thick. How do I know? Because that's the thickness of a piece of card. I've also photographed the slit with a ruler next to it to double check that is actually the size of the slit, 0.14 millimeters. And some of the light goes straight through and produces this broad central region, which is about 3 centimeters or so wide. But we're interested in how far it is from one dark spot to the next dark spot in the zebra fringes. And of course, that would be just half based on the principle that the central spot is just twice as wide as all the others. So I'm interested in this angle because the wavelength of light divided by the size of the slit determines what that angle theta is. And so no awkward trigonometry here. Because I've got a fairly large distance between the screen and the slit of about 3 meters, then roughly speaking, that angle is simply 1.5 centimeters divided by 3 meters. It's a simple trigonometry of a very narrow triangle. And so using that, 1.5 divided by 3 meters should give me the wavelength of light divided by the size of the slit. So let's do the numbers. The angle is 1.5 over 300, working in units of centimeters. And so the angular separation of the fringes that we've just found should be the wavelength of light divided by the slit width, or lambda, the thing we're trying to find, the wavelength of light, divided by 0.14. So let's just multiply that by 0.14, and we get an answer that the wavelength of light in this particular red laser is measured to be 700 nanometers. Not quite right, because I know it should be a little bit less than that. I happen to know what this red laser lambda is, mainly because it's written on the side of the laser, but that's obviously not what the demonstration was all about. I know that the answer should be about 650 nanometers. So again, just like the speed of light, we've ended up with a bit of an overestimate. We're about 10% too high. But still, we have shown that the wavelength of red light is less than 1 micron, about 2/3 of a micron, and we get the answer to be approximately 700 nanometers. We will see shortly that we can verify the other end of the spectrum. If we look, as we will do shortly, through a diffraction grating, we can verify that the blue end of the spectrum is about half of the wavelength of the red end of the spectrum. So having measured red as 700 nanometers, then we can also show that blue is about half that, about 350 nanometers. So we've measured the range of the visible spectrum by doing this particular experiment of shining a laser through a slit, and we'll see the range of blue to red shortly. Okay, let me switch that laser off rather than run the batteries down. You can always see that again later if you so wish. Back to the man in the tie and the audience of 5. Okay. Right, so now we're going to think about diffraction gratings. Whilst I prattle on for 1 or 2 slides about diffraction gratings, would it be possible if someone or more than one person actually handed out these diffraction gratings to the audience? I should have mentioned this earlier. Would some kind volunteer? You can have one of those lights, the left-hand light perhaps. Yeah.
Did you measure that then?
Could you take some, or just hand out a bunch and let them pass it back? So for the time being, just hang on to the diffraction grating. Don't do anything with it. God, you're like a 5-year-old. You start playing with it as soon as you get it, don't you? Just hang on to it for the time being, and I'll tell you when. Okay, a diffraction grating is either a piece of glass or possibly a piece of plastic on which you have regular rulings like this, not necessarily exactly that shape, but there's a regular engraved set of lines that are similar to, but not quite the same as the wavelength of light, and they will produce interference of lots of different waves. They will produce diffraction. That's why it's called a diffraction grating. A diffraction grating acts a little bit like a prism, but it's different in 2 ways. One is a prism will refract the light and produce a rainbow in one direction, depending on which way up you've got the prism. But a diffraction grating will send light in both directions, and so you'll end up with a spectrum, a rainbow, on either side of the main light source. Notice also it's backwards. The prism will generate red closest to the line of the original light and blue further away. But the diffraction grating, the blue will be closer and the red will be further away. I don't know what these lights are. Okay. Oops. If you, has Moti got one? Is it still coming across? Oh, right, okay. Okay, for the right-hand side of the audience, if you just have a look at the lights above you at the moment, you see a continuous spectrum. You see, just hold it up to your eye. Hold it within a centimetre or so of your eye. You'll get a confusingly large number of spectra because there's a lot of lamps in this particular ceiling. But I hope you can see that you've got a spectrum on either side. For every light source, you've got a spectrum on either side, and the blue is closer than the red to the light source. Yep? And the blue is about half the distance to the red. So the red, we know, is about 700 nanometers, so the blue is about half that. The blue is about 350, maybe a little bit more than 350 nanometers. Have the diffraction gratings made their way across okay? Anybody missing one? Okay, right. So it's similar to, but not quite the same, as a prism. A prism works by refracting the light. A diffraction grating works by interference. So it's not the same phenomena. It's not the same phenomena, for instance, as a rainbow, which is a result of refraction through raindrops, rather than diffraction, which is a result of interference. So regardless of the diffraction grating that happens to be in your hand, you've all seen diffraction gratings anyway. If you look at a CD or a DVD, that's effectively a diffraction grating, because the tracks that make up the music or the data are about a micron or so apart, and therefore they behave like a diffraction grating, because the tracks will produce reflections of light which all interfere with each other and give you those familiar colours. If you wish, you can actually use a CD to make a spectroscope for yourself. If you didn't have a diffraction grating handy, just grab yourself any CD. Doesn't have to be ABBA, doesn't have to be anybody, just any CD, and then you can make it into a spectroscope by following the instructions at the bottom of the screen there, which you can pick up in the handout if you so wish. You've probably also seen diffraction in other contexts, because, for instance, if you look at a butterfly wing, the actual structure of a butterfly wing is tiny, tiny structures within the wings that are, again, comparable in structure to the wavelength of light, and it produces interference and hence strong colours, even though there may not be any pigment in that particular part of the butterfly wing. Okay, so that's the introduction to diffraction gratings, and now we're going to have a demonstration. What we're going to do is, I was going to make a spectrum using a prism. Let's see if that works with the projector as it is. I'm not sure if we'll need the lights down. Let's just see if we can get it to work regardless. If we can throw a... Okay, you can see, okay, above the screen to the left, okay, you can see, whoops, missed. Okay, you can see a little bit of a rainbow there. Red is on the inside, blue is further away from the screen, so that's what a prism is doing. But we are going to now look at what a diffraction grating can do, and then we will look at different light sources. So can I have the lights off completely, please? Okay, can you hold up your diffraction gratings? Hold it a centimetre or two in front of your eye, or just touch your glasses if you're wearing glasses, and have a look at what's on the left-hand side of that white line. Hopefully there's no other light sources here that is going to make life too complicated for us. You might have to just hold your hand up to avoid any light coming in from the doors to your right. Anybody on the right-hand part of the audience? Thank you very much, sir. Hopefully you should see the result of the diffraction through of that white light. In other words, what I hope you see is something that looks like that. Not necessarily in that position. It probably will end up perhaps further over to the left of the screen, as far as depending on where you are. If you're sitting at the back, it'll be a long way to the left of the screen. If you're sitting at the front of the audience, it'll probably be somewhere where this curtain is, something like that. Where I'm standing at the moment, you should see a spectrum. Does everybody see that? Okay. What do you see if I change the screen to that? What do you see over on the left-hand side? Again, if you hold it up to your eye and look straight ahead, do you see the spectrum from white, the spectrum from red, the spectrum from green, the spectrum from blue, and the spectrum from white again? Does it make any particular shape? S. There you go, my initials. So you can see my initials, because what you're effectively doing is looking at the whole spectrum of white light, which is all of the colours, the spectrum of red only, which gives you the red, the spectrum of green only. Notice it isn't green only, there's a little bit of red and blue in there. The spectrum of blue, and then the spectrum of white again. If I just kill that and you have another look, you should see an S over to the left-hand side, probably off the screen, maybe over here somewhere. You should see a big S because of what you're looking at on the screen. Yep. Okay, excellent. So what we're now going to do is, let me just make sure, we saw it from the lights up there just a second ago, but let me kill the PowerPoint. If you have a look at that, that should look very similar to what you saw in the ceiling. It's just that as there's a single light rather than lots of lights, and so you should get a very clear spectrum on both sides. Yep. Okay, so that's enough of that. Let me kill that to avoid shining in everybody's eyes. Maybe I'll just leave it on the first setting so you can refer back to that. What is interesting is what you see if you look at the spectrum not of that light source, but the light source over on my left-hand side. What do you see if you look through your diffraction grating and look not at this light, look at the screen itself. Look forward. What do you see when I switch this light on? Oh, that's the correct response. Yes. So you should see this particular fluorescent light is a hairpin shape, which I blanked off half of it. So you're seeing a sort of a shepherd's crook or a walking stick sort of shape to the lamp. And maybe it would be better if this doesn't get in the way, so let me just kill this. Okay, and again, you might want to just hold your hand up to make sure you don't get too much coming in from the corridor. But if you look straight ahead, you should see a whole load of walking sticks. Everybody see that? A very bright green one. Yep. A fairly bright red one. A fairly bright blue one. Maybe you see a cyan one in there as well, but it looks a little more blurry. And you see a whole load of orange ones as well. So unlike the light source we were just looking at, or the light source in the ceiling, we are not seeing all the colours of equal intensity. There are some colours that are very pronounced and other colours that are hardly there at all. Perhaps you can see pretty much all colours, but some are distinctly very much brighter than the others. What you are looking at is individual atoms in that light, producing light of very specific colours. Let me just show you what you're looking at, and then I'll show you, let you have another look at the original light source. What you're looking at is the light there produces a spectrum on both sides. Let's ignore the one on the right for the moment. If we just concentrate on the spectrum on the left-hand side and blow it up a little bit, I hope you saw something that looked a little bit like that. Very bright green, bright red, bright blue. There's some cyan in there as well, other colours, and certainly a little set of oranges as well. The point is that they are particular colours corresponding to particular wavelengths, and we can identify which atoms produce those particular colours, because we understand quantum mechanics, which tells us how atoms are put together, and we'll see shortly how it is we go from atomic energy levels to light. But the point is we can identify which atoms produce which colour. For instance, that very bright green is from mercury, so is the blue. The red is coming from europium, the cyan is coming from another rare earth called terbium. So in that fluorescent light bulb, inside this particular beastie here, there is mercury vapour, a bit like you see in mercury streetlights. If you still happen to have those outside your house, maybe they've been replaced with LEDs these days. But a mercury streetlight works on the same principle. There's a very bright mercury line, which is green. If that's all there was in the lamp, the light would be a horrible colour, and if you wanted it as a reading desk light, you would end up reading pages that were all coloured green. So the manufacturers have taken the mercury vapour and said, well, mercury is very strong in the green. What if we add a few rare earth atoms which will glow in the red or in the cyan? Then it'll help balance out that colour, and if you just use your eyes on that, you can see that it looks roughly white. In other words, it looks a reasonably natural colour. It doesn't look horribly green, even though the brightest line in the spectrum is quite obviously green from the diffraction grating. So the manufacturers simply add atoms into the lamp in order to give you a nice red, green, blue balance so that you perceive it as, yep, that looks like a nice white colour for my reading lamp. And that's how LEDs are produced as well, balanced to try and give you a reasonable balance between red, green and blue, though the spectrum doesn't look quite like that. So we can see that physically that lamp is very different from the other one we've just seen, because we have very distinct lines corresponding to particular atoms. So you can tell what that lamp is made of, even though it's 10 meters away. But if you can do that by sending light through a diffraction grating and then identifying from the colours which atoms are present, what does it matter if the lamp is 10 meters away, or whether you're collecting light through your telescope and sending it through a diffraction grating, in which case you can tell what atoms are in a star 10 light years away, or what atoms are in a galaxy 10 million light years away, or 10 billion light years away. There is no difference at all. The fact that it's sitting in the same room is irrelevant. If you collect the light and split it up, then you stand a good chance of being able to identify which atoms have produced the light that I am now seeing. And that is basically how we know what stars are made of, because it is possible to do spectroscopy. Imaging is absolutely fantastic, but an image just tells you what something looks like. If you want to know what it's made of and what it's doing, you look at the spectrum of an object, and then you get a much better idea of what's actually going on in that particular object that you're looking at. Okay, you can either hang on to the diffraction gratings or you can hand them back later if you like. I am very happy if you wanted to take them home and start looking at all the lights in your house and the street lights outside your house, trying to work out whether you've got mercury street lights, sodium street lights, LEDs, have you got fluorescent bulbs, have you got halogen lamps. All of them will have different spectra, and you're welcome to take that diffraction grating home and do a little bit of physics for yourself, or pass it on to your kids if you don't particularly want to do that for yourself. Okay, so back to the PowerPoint again. So light is an electromagnetic wave. What we mean by electromagnetic wave is it's a combination of electric fields and magnetic fields, as worked out by James Clerk Maxwell. The most famous thing to come out of Scotland, either firstly or second only to Scotch whisky, perhaps. So we understand the nature of light based on these electric and magnetic fields. I'm not going to go through what James Clerk Maxwell actually did, but we understand that light can behave as per that picture, with electric fields going side to side and magnetic fields going up and down. Whenever we talk about waves propagating, we prefer to think of something wiggling, going in the direction of the stick and wiggling up and down. And the electric field might be going up and down and the magnetic field might be going the other direction. But whenever we have a picture of light, we sort of ignore the magnetic field because it just makes it very difficult to draw for no other reason. We know it's there, but if we want to represent what's going on with light and we talk about whether the electric field is bouncing up and down or wiggling up and down, or whether the electric field is wiggling side to side, we know there's a magnetic field as well. So we don't need to draw it because we know it's there. We know it's an electromagnetic wave. We don't have to draw it in. So this particular picture has got electric and magnetic waves, fields drawn in. But from now on, I'm just going to ignore the magnetic bit because it just gets in the way. And I'm going to talk about whether or not electric fields are doing that or doing that. And we call that orientation polarization. Are the electric fields trying to make electric charges go up and down, or are they trying to make the electric charges go backwards and forwards as they travel through a medium, for instance? So we call that linear polarization, and you're probably familiar with that in the sense of Polaroid sunglasses will take light which is going in any old direction, and it will only allow through light that is wiggling either up and down or left and right, depending on how the sunglasses have been made. But what I want to point to now is another interesting aspect of polarization, and that is it is possible to take light that's polarized like that, and if you add the light together with another beam of light in a particular way, which I'm not going to specify, look it up on Wikipedia if you're interested, it is possible to make light do other things. It is possible to make light corkscrew. It is possible to make it, if you like, helical, such that instead of just going up and down or just going side to side, it continually rotates as the light propagates, as indicated by these little black arrows there. As the light traverses along that direction of propagation here, the direction in which the electric field points corkscrews. The magnetic field is doing the same thing, but we don't want to draw that because it really does get too confusing. So we call that circular polarization. And that is a very interesting phenomena because some of you might be familiar with the idea of circular polarization based on photography. You might have bought yourself a circular polarizing filter. Nothing to do with the fact that it's round. It's based on the fact that it's letting through light that is polarized in this particular way. So let's have a little demonstration. We're going to pass light through some polarizing filters. I'm probably going to skip this one and invite you to come down and have a look at the calcite crystal for yourself on the play table. And we're going to have a quick look at polarizing filters. And again, I'm going to invite you to look at this for yourself. It's a difficult thing to actually show with a projector. For technical reasons, projection light, this light itself, is actually polarized and it gets in the way of doing any simple experiment. But I'll just tell you about the demonstrations that you can come and see in a little while. What we're going to do is to take some polarizing filters, and what we've got is some polarizing filter material that will only let through light if it's wiggling backwards and forwards horizontally, like that. And we're going to take another piece of material which will only let through light if it's wiggling that way, vertically, so-called horizontal polarization or vertical polarization. So one will let through one and one will let through the other. And if you put them like this so that one is horizontal and one is vertical, well, light can't be both. It's either doing horizontal or vertical or some other angle, but it can't get through both. So we call this crossed polarizers, so nothing is let through. And the question then is, what if we take a piece of acetate? It's a piece of acetate with a few bits of sellotape on it. I'll talk about the sellotape in just a second. And we're going to place that in between the two crossed polarizers. So let's see if we can get that to work. Let's go back. Hopefully the iPad hasn't switched off. Okay. And I could do with some light. So let me take the light I used before. And let's see if we can see what's going on here. Is that enough to see what's going on? Let's have a look. So I'm going to possibly block somebody by standing here. But if we take a piece of polarizer, it reduces the light, but not by much. The other one reduces the light, but not by much. But if I put the two together, then basically, if they are like this, they should block the light coming through. In other words, we effectively can't see any light coming through now. Let me just adjust that slightly. Okay. So if I were to rotate them so that they're letting through the same thing, I get some transmission of light. But if I rotate them so that they are only letting through one horizontal and one vertical, let me just clamp those together so I don't have to keep adjusting them, then essentially nothing is let through. It's effectively black. So if no light is getting through these two filters, which I'm now not going to touch, what would happen if I put a piece of plastic, a little bit of acetate, in between them? If no light is getting through, then surely it can't actually make any difference if I put a piece of sellotape or a piece of acetate in between those two. But what happens if I take that in which no light is getting through and then insert a bit of acetate? Suddenly light gets through. And notice that you can see individual bits of sellotape. Whoops, let me just drop it slightly so it's in camera. You can see that the sellotape is producing different colours because we're producing interference, which is constructively interfering some colours and not others. If I rotate the sellotape, you can perhaps see that the colours change. This is more convincing if you do it for yourself on the play table, so I'm just trying to give you an idea of what's actually going on. So if I take the sellotape away, it goes back to being basically just black. So by adding another filter, we actually let more light through than just having the two in the first place. Adding a third piece of plastic lets more light through. How can that be? If we have a situation where, as I've shown in the, let's jump back to the PowerPoint. If we have a situation where light of one polarization is being blocked by one filter and light of the other polarization is being blocked, what's actually happening is the sellotape is taking light that is horizontally polarized as it comes through that back polarizer. The sellotape is actually twisting the light round so that it's now not necessarily vertical, but it has a component which is now vertical, which can now come through the vertical railings. If you want to think of the polarizer as being a set of railings which will only let through oscillations of a particular direction. So the colours you see are a result of how much that light is twisted. Thicker pieces of sellotape, i.e. lots of sellotape on top of itself, actually produces more of a twist than only one piece of sellotape. Two pieces of sellotape, one on top of the other, produces a little more. Three pieces of sellotape, even more. And because it's twisting the light, it's letting more and more of that light through. And the nature of the sellotape itself, it's a piece of plastic which is actually changing the polarization. Plastic is a molecule which has a particular direction. That's why it affects the polarization of light. And I invite you to come and have a play with that afterwards. So that's what I've just done. That's what you would see if I could hold it steady enough. That's what you'll see for yourself if you come down to the front. Basically, each different piece of sellotape, I've just put lots of pieces across so that each of them is a slightly different thickness. The colours are there because some wavelengths will reinforce and some wavelengths will cancel, and it will be different for different thicknesses. Hence, over here, it happens to be green that's reinforced and red is missing. Over here, blue is reinforced and green is missing, etc. Hence the different colours. If you've ever seen a geological sample, a rock sample that looks extremely coloured, that's not the rock itself. So just like this piece of sellotape basically is virtually transparent, so if you take a piece of rock and cut a thin sample, it's effectively transparent, but if you put that piece of rock under a polarizing microscope and use filters as we've shown here, then you can reveal the structure of the rock and see the grains and see what it's made of, because each piece of rock will again rotate or change the polarization by a certain amount. This, I will let you come and have a look. This is a piece of calcite, which is a crystal, which again affects the polarization of light, and you'll see what it does. If you come down and have a look for yourself, it doubles up because there are two paths of light through the crystal. The speed of light actually depends on whether the light is traveling like that or whether the light is traveling like that. Two different light beams, even if they're trying to go in the same direction, they will travel at different speeds. The speed of light is different for those two polarizations in some crystals, including this one, so come and have a look at it later. Another peculiarity of polarization, here's vampire zebras. I'm not sure if you knew that some zebras are vampires. Okay, so there's a picture of some zebras I took when I was on safari, and there's a reflection in a window. The reflection clearly shows the monitor and some lights behind it, and the chair over here is reflected in the window, as are various other things. But the vampires have no reflection. The zebras, in this case, have no reflection. And again, I invite you to come and have a look at an example of vampires with no reflections up here on the play table. Did you know that some beetles are left-handed? No, I'm not talking about Paul McCartney. Let's change the beetle with an A to beetle with an E. Some beetles are left-handed. So I have some glasses here. They're on the play table at the moment. I have some 3D glasses which the left-hand lens will only let through left circular polarized light, and the right lens will only let through right circular polarized light. If you look at this beetle with left circular polarization, you get these beautiful metallic colors. If you look at it with right circular polarization, the colors have vanished completely. Some beetles only produce left circular polarized light. So it's not just a very abstract concept that James Clerk Maxwell came up with when he described the nature of electromagnetic radiation. Some beetles look very different depending on whether you're looking left circular polarized or right circular polarized. Is the light spinning anti-clockwise or is the light spinning clockwise? I have no idea why these beetles behave this way. Is it something to do with mating? Is it something to do with avoiding predators? Is it just a byproduct of the way the molecules are put together in the carapace, in the backs of these beetles? I don't know, because not all beetles look like this. I brought an example of some beetles that have this particular effect of producing left circular polarization, and just for comparison, I've also brought along a beetle. They're all dead, by the way. I brought along a beetle which doesn't show the same effect. So again, I invite you to come and have a look. So, given that time is getting on, and I know we're all desperate for a cup of tea, and desperate for a play on the table as well, let me finish by saying a few things about atoms and light. Okay, electromagnetic waves, light, ultraviolet, infrared, and possibly other wavelengths as well, are generated whenever charged particles are moved around. If you take a charged particle in the middle of nowhere and wiggle it, you will generate electromagnetic waves, because if you take an electron, for instance, a charged particle, it generates an electric field. If you then wiggle that particle, that wiggle will effectively generate waves which go away. So electromagnetic waves can be generated by moving charges. One situation where charges are moving is a particle accelerator, so you can generate light by sending particles through a particle accelerator. But of course, one classic example of charges that are moved around are charges within an atom. So to understand how light is being generated, for instance in that fluorescent light over on the right hand side, let's have a think about how atoms are put together. So we can think of an atom as being a nucleus. It doesn't matter, but okay, it's positively charged in the nucleus, and a whole load of negatively charged electrons buzzing around like bees in a hive. That might be how we think about atoms, and it's a perfectly pleasant way of thinking about it, but it has the disadvantage that it doesn't make it clear that all the electrons will have different energies. Here, all the electrons look equivalent to each other. They're all orbiting at the same sort of distance. It's like having a solar system where all the planets are at the same distance from the sun. So it doesn't really give us a proper indication of the fact that in any particular atom you choose, the electrons will all have different energy levels. And that's a somewhat better way of thinking about an atom. You can think about a nucleus, and you can think of sets of electrons orbiting in some sense. It's not quite a solar system, but that's a good enough picture for the time being. You can think of the electrons orbiting at different distances. And you can either think of it like a solar system as being planar, which again is not quite right. It's better to think about them in concentric shells, a bit like a Russian doll, where you have some electrons close to the nucleus, and outside those another shell of electrons, and outside that another shell of electrons. If the electrons are all at different distances from the nuclei, then they'll all have different energies, and that's the important thing. If we just think about two energies, a low energy and a high energy, let's not worry about exactly what those are. If an electron is in a high energy, it can fall down until it reaches a low energy. In other words, it can jump, a so-called quantum jump, from one to the other. What it doesn't do is slowly go from one to the other, such that if you happen to catch it halfway, you would find it halfway between one energy level and another. As far as we can tell, quantum jumps are effectively instantaneous. An electron might appear to be in one place, and then a fraction of a second later, it appears to be in a different place, in a different energy level. But at no time can we catch it halfway between. It doesn't seem to continuously move from one to the other, as Newton would be happy with. No, atoms don't behave the way Newton would like. These are quantum mechanical objects. And if we start with with electron in a high energy level and it drops to a low energy level, what happens to the energy that's lost? That is what comes out as electromagnetic radiation. A packet of light, a so-called photon, comes out of the atom. And similarly, if we've got an electron in a low energy state, a low energy level, and we shine light of just the right energy, in other words, if we give it just enough energy to go from there to there, then light coming in can be absorbed by the atom, and as a result, the electron jumps instantaneously from the low to the high. Again, it doesn't spend time getting there and then finding, oh, it's not quite the right energy. What it can't do is absorb a photon, a packet of light, that's of the wrong energy. You can't have the electron spend its time getting 90% of the way there and then say, oh, I haven't got enough energy, I'm going to have to go back again. It doesn't work that way. It's all or nothing. Either it's the right amount of energy to make it jump from there to there, or it's not. And hence, if you know that an atom has particular energy levels, then you can predict what wavelengths or energies or colours of light that atom will produce. And effectively, we were doing that backwards when we were looking at the fluorescent light on the right-hand side. We were looking at particular colours of light and deducing if it's green, then it's a particular energy. That corresponds to this energy, and that we know is the energy of a mercury atom. So in other words, that's the link between what we know of colours and what we know of energies. A physicist will quite happily talk about a particular colour being a particular wavelength and also being a particular energy. The packets of light aren't entirely arbitrary. They're a particular size. Photons come in particular sizes, if you like, such that we know that a packet of energy that corresponds to red light is a lower energy than a packet of energy that corresponds to blue light. So we can talk about an energy scale, we can talk about a wavelength scale, or we can talk about colours. And as far as a physicist is concerned, they're essentially interchangeable in the sense that if we know one, we can work out the other two. If you give me a colour, I can work out the wavelength and its energy. If you give me the energy, I can work out the colour and the wavelength. Given one, you can work out the other two. So it doesn't really matter whether we're talking about colours or wavelengths or energies. And so if we can identify atoms having particular energy structures, and that's what quantum mechanics is all about. Quantum mechanics gives us a recipe that says this atom should have these energy levels, helium should have these energy levels, beryllium should have these energy levels, mercury should have these energy levels. If we know what the energy levels are, then we know what to expect when that atom either emits light or absorbs light. If it emits light, just like we saw with the fluorescent light on the right-hand side, we will see characteristic light on a, not necessarily black, but on a dark background, we will see bright lines. If that collection of atoms there was absorbing light rather than emitting light, then we would see a spectrum with particular dark lines, but again, in characteristic positions within the spectrum. If we look at a spectrum and we see lines, we just measure where they are, measure their wavelengths, compare with quantum mechanics. That tells us the atom that produced that particular spectrum must be this particular atom in the periodic table, or possibly collections of atoms, i.e. molecules. And so that's how we get fireworks of the right colour. We just put atoms in, where the atoms we add to a firework are atoms with the right energy levels to give you the colour you want when it goes bang, basically. So you can see red comes from strontium, yellow comes from sodium, green comes from barium, etc. You can make any firework colour you like, almost, just by mixing and matching the atoms that have the right energy levels to give you those colours. And for astronomers, perhaps you recognise this, I took a diffraction grating and took an image of M57, the ring nebula. The direct light is fairly weak, but most of the light has actually been put into the spectrum. And the spectrum, you notice, well, the stars look a bit odd, but the stars are producing these spectra that are zooming off in that direction. But the spectrum produced by the ring nebula is in this direction, and you see nothing, 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 and then you see a very distinct cyan-coloured image of the ring, and then you see nothing, 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 and then you see a red image of the ring. In other words, its spectrum is effectively nothing, and then a spike of cyan, and then nothing, and then a spike of red. And if you look at what those wavelengths are, you can deduce that that has come from oxygen, and that has come from hydrogen. So just by taking an image of an object and looking at its spectrum, we now know that the ring nebula is made of hydrogen and oxygen. No ifs, no buts, we know that is the case. Doesn't matter how many light years it is away, doesn't matter how small it is, doesn't matter how faint it is. Once you've got the spectrum, you know what it's made of. And so putting a spectroscope on the back of a telescope is an enormously powerful way of doing research. Not necessarily that popular with amateurs. Most amateurs like the idea of taking pictures. Nothing wrong with that. Producing images is fantastic. But an image only tells you what something out there in the universe looks like. It doesn't tell you what it's made of, and it doesn't tell you what it's doing. So if you have a spectroscope, perhaps as well as a camera, then you have an enormously powerful tool. So here's a star analyzer, very similar to the diffraction gratings that I've handed around, except it's mounted inside a 1 1/4 or a 2-inch eyepiece filter thread, such that you can put this into an eyepiece and then look at the spectrum of any object. Rather than put it in a telescope, I took that diffraction grating, put it onto the front of a telephoto lens with a bit of masking tape and a bit of, not chewing gum, a little bit of blue tack and a little bit of masking tape. I put the diffraction on the front of a telephoto lens, went into the back garden, pointed it at Betelgeuse, and took a 10-second exposure of Betelgeuse with a camera, not tracked, there's no need, it doesn't matter if the star moves slightly. And I obtained the spectrum across the top there, the spectrum of Betelgeuse taken with a diffraction grating and a normal camera. We can see various dark lines in the spectrum. If we plot the intensity as a function of the wavelength from the blue to the red, we find that there's lots of spikes in there, and by lining up those spikes and checking a table of numbers, we can actually determine that there's some helium in the atmosphere of Betelgeuse, there's some titanium oxide, there's some sodium, there's some vanadium oxide, and perhaps most worryingly for Betelgeuse, there's some iron. Those of you who know your physics know that when you start fusing elements together, you can't go beyond iron. When a sun or star starts producing iron in its core, then it's running out of fuel. And a red giant like Betelgeuse is quite definitely running out of fuel. Some of that iron has actually been churned up and is starting to appear in the atmosphere. This is a precursor to, it won't be that long before Betelgeuse goes supernova. That long could be tomorrow, it could be in a few thousand years, it could be in 100,000 years, but of course that's very short on a time scale of billions of years of the lifetime of most stars. So the point is that you can see what Betelgeuse is made of in a 10-second exposure with a diffraction grating on the front of your camera. If you want to take your diffraction grating when you've given up on looking at your LED lights and your street lights, if you want to put it in front of your camera and take a picture of a star, by all means do, and see if you can get the same sort of results of telling what a star is actually made of. At the very least, you'll be able to tell quite distinctly the difference between a red giant and a hot blue star, for instance. The spectra will look quite different. So telescopes, of course, over the ages have evolved from very small telescopes of Galileo and Newton of a few centimetres in size up to huge great leviathans, and the pressing need is always to gather more light. So yes, larger mirrors gather more light, but because of what we said about diffraction, large mirrors give you sharper images. So you get a double whammy. A large mirror gives you not only brighter image, it gives you a sharper image as well. But remember that one of the most important things to do with any big telescope is to make sure you stick a spectroscope on the back end rather than just a camera. So these things will be coming along shortly, like the European Extremely Large Telescope, hopefully completed in not more than a few years now. If you haven't got the scale yet, there's 2 people standing on the Naismith focus there and a couple of people down at the front there. So that gives you an idea. Something like 40 meters or so in diameter. It's not actually circular, it's a whole load of, it's a segmented mirror, a lot of hexagons, but it gives you an idea of the scale. But just to remind you that this is not just a very big telescope for taking images of galaxies a long, long away. Basically, the ELT, for instance, has, I think this is still the plan, to have 3 different types of camera for imaging, but 7 different types of spectrometers or spectrographs for getting the spectra of objects. That's a reminder of just how important it is to know about the nature of light and know about the spectrum of an object. It's not appreciated perhaps that Hubble is similar in that Hubble has got more spectrometers than it has imaging cameras, because it is so important to be able to tell what the spectrum of light from a distant object, a nebula, a protoplanetary system, a star, a galaxy. We've come a long way in the sense that it wasn't that long ago that Augustus Comte, back in the late 1700s, early 1800s, was saying the stars are just too far away. They're pinpoints of light. We will never know the composition of the stars. Within a few years, spectroscopy was born, and now, quite definitely, we do know the composition of the stars because we understand the nature of light. So, I hope you now have a better understanding of how light works. You've seen demonstrations that have shown that the speed of light is 300,000 kilometers a second, give or take 10%. You've seen a demonstration that the wavelength of light is 700-ish nanometers for the red end, and the diffraction grating has told you that the blue is about half of that. And so we've seen how the diffraction grating works and splits light into its component colours, and that allows us to look at the composition of objects. And you've seen that light can be polarised in different ways and give rather interesting effects, whether it be linear polarisation, circular polarisation, whether we're looking at sellotape or whether we're looking at beetles. So I hope you found that interesting. Take the diffraction gratings away with you, go experiment for yourself. Now go have a cup of tea, and in a few minutes' time we'll come back to the play table and I'll show you some more demonstrations.
Stuff first.
Yeah. Yeah. Thank you.
Reflection of the vampire. It's an nanometer exactly. It's 1,000th of a micron. So what do you want? A nanometer is nano. Nano is 10 to the minus 9 meters. So a millionth of a millimeter. 1,000th of a micron. So tiny. Yeah, tiny. Okay. Yeah. Let me switch the lights on.
So what's this one? This image contain this polarised yeah. And the diffraction disappears. You said
in the old days, very fine
polarisation classes. I was saying
diamond slide off the diamond sliders will do the same, and then use the fraction of this tiny these days they're made by hologram. You actually generate an interference pattern which then etches in so these ones I did really make a hologram. And you can buy them by the meter if you want to. If they are now. Now with the polarizer, I just slowly rotate the polarizer, about the pairs of One angle you see on, another angle you see over the other. So those are polarized differences. And how it's like separated, polarization and then coming through. Actually, the speed of light is different. One set of light is coming through that way, another set of light is coming through that way. So the speed of light for those two light beams is different. And one makes it to the surface before the other. If you can't see one, then maybe not. But at the end of the